Good morning. I'm Christine Sau. Welcome to this news briefing from the 250th National Meeting and Exposition of the American Chemical Society in Boston. We're joined today by Dr. Zhichao Hu from Rutgers University. He's going to talk to us about new technology that will bring us more sustainable, less expensive LEDs. Dr. Hu.
Thank you, Christina. Good morning, everyone. I really like to thank ECS for this wonderful opportunity to talk to all of you about our recent development with rare earth-free phosphors. Speaking of LEDs, especially white LEDs, it's a very familiar concept to a lot of us because this Nobel Prize-winning technology is making its ways into our homes, offices, and schools, and you can see LEDs everywhere. But not a lot of us know how to make a white LED. There are basically three different ways of making LEDs, as you can see on the slide. So you can either take three chips. You can take the blue, green, and red chips and incorporate them into a single white LED. That's a multi-chip LED. And the combination of the three colors, the RGB colors, would give you white. And this technology is rather, by having multi-chip in one LED is rather expensive. So a lot of the LEDs on the market are actually not manufactured this way. And there are two alternatives. They're called phosphor-converted white LEDs. So instead of using multi-chip technology, you can take a one-chip LED, you can take an UV LED or blue LED. For example, in the middle here, I have two examples of phosphor-converted white LED based on UV chip. So you can use an UV LED and you can quote material called phosphors. Phosphors are materials that emit light. So you can either quote the three different color phosphors, the RGB phosphors, onto a UV LED, or you can coat a white phosphor onto a UV LED, and the excitation from the UV energy would excite the phosphor, and the phosphor emits light, and that also gives you a white LED. And the last way to make a white LED is probably the cheapest way. I'm saving the best to the last. So you can take a blue LED. Blue LEDs is very easy to make and relatively cheaper. And you can take a blue LED and quote yellow phosphors. And the combination of the blue light and the yellow gives you white. So the key component here that transforms a blue LED into white light is the phosphor. If we look at commercially available phosphors now, they're all, most of them, I would say, majority of them, rely heavily on rare earth elements. And as the name indicates, rare earth elements are expensive. If you look at three key ingredients of commercially available phosphors, for example, yttrium, europium, and terbium, the price of these three elements went up the roof in the last decade. And there is an estimate from the US Department of Energy. From 2001 to 2011, the prices of yttrium, europium, and terbium went up by 400%, 600%, and 1,600%. So really, as you may experience in a supermarket, if you look at an LED bulb and an incandescent bulb or a compact fluorescent bulb, you can see the LED bulb is much more expensive than the conventional bulbs. And a lot of that comes from the phosphor, the cost of the phosphor. So the motivation of our work is really to reduce the cost of phosphors and try to get rid of rare earth elements. So we have technology that allow us to combine organic and inorganic ingredients. We combine fluorescent molecules and some inorganic species, and we can make phosphors that emit different colored lights. But these materials are free of rare earth elements or elements such as cadmium or selenium. And cadmium is the main ingredient for quantum dot-based lighting material. And selenium is also a main ingredient for quantum dot-based lighting material. But those two elements are rather toxic, and we want to make our phosphor green. So our phosphors actually don't contain any rare earth elements, nor cadmium or selenium. Is 100% environmentally friendly and sustainable. And some of the phosphors we develop in our lab, there a rough estimate that we can cut the price of the phosphor by nearly 90%, the cheapest material in our lab. So if you look at my slides, and this is an example of a white phosphor that under UV illumination shines white. And if we move on to the next slide, this is an example of how to transform blue light into white light. So I have a blue LED, I actually have blue LED and a bulb or a plate. Then I can coat our yellow phosphor onto the surface of this bulb or plate. And I also like to mention that our material is really easy to apply to different kinds of surfaces. For example, you can see on the left column, I have my material coated on a plastic surface that's bendable and flexible. And if you shine blue light, you can see the phosphor glows white. And moving on to the next slide, we have hybrid phosphors. We have a lot of phosphors in our lab. We have a long tradition developing these phosphors. And I have a bunch of different colors and coated on LED bulbs that basically we have phosphors cover the entire visible spectrum. And I brought with me a demo today, and I'm going to show you how to convert a blue light into different colored lights. So if we can dim the light. So as you can see here, I have a blue light, and I have 4 examples of the phosphors we develop in our lab, and we coated the phosphor onto a transparent plastic cap, and then I can put the cap on top of this blue light. I don't know if you can see this clearly. So the blue light excites the phosphor and gives you a different color. And the first one we see is a blue phosphor. And the next one we're going to see. So this is what it looks like, the cap with the phosphor coated. I'm putting on top of that excitation source, and this is a yellow phosphor. And I also have a green. This is actually a greenish yellow. And the last one I'm going to show is a cyan or light turquoise. So these are just the few of many phosphors we have in the lab, and they're all free of rare earth elements or toxic elements, and they're a lot more environmentally friendly and sustainable than the commercially available rare earth containing phosphors. And the cost of these phosphors are significantly cheaper.
Can you put the lights back up, please?
And that's pretty much what I have. I'll be happy to answer any questions.
Great, thank you so much. Do we have any questions? Yes, Ben.
Ben Valsler, Chemistry World Magazine. I'm wondering about the manufacturing process. So at the moment, we know that the compounds we're using are quite expensive, but we have the benefit of scale, and LEDs are in mass production. Will your phosphors be able to be sort of slotted into the same manufacture process, or will it need something new?
That's a very good question. So we can actually compare the different syntheses of commercially available phosphorus and our phosphorus. And a lot of the commercially available phosphor, they are solid state compounds, meaning that they need high temperature to form the structure. And actually, a lot of phosphorus we develop in our lab require much mild milder conditions. For example, we have phosphorus synthesized under room temperature. So you only need to mix the ingredients and give it a stir. So we haven't done a production level synthesis, for example, like kilograms or tons. But I can imagine it's not difficult to incorporate the process into industrial scale.
Thank you.
Thank you.
So it's Kath O'Driscoll from Chemistry and Industry magazine.
Good morning.
Can you say a bit more about the compounds that you're using in the phosphors? What specific compounds and how do they emit these different colors of light?
Okay, so there are two types of materials. By broader definition, they're actually the same, but we like to differentiate within our lab. One type is called metal organic framework or coordination polymers. They are made of fluorescent organic ligands and inorganic nodes. For example, a lot of the metal organic phosphor we study are based on zinc and fluorescent molecules. So the zinc serves as a node, connects the organic molecules. So what we are doing here is we're trying to immobilize the organic molecule into a rigid framework, and the metal node is the glue. So that's one way. The other way is what we call hybrids. They are made of inorganic species, a bulk inorganic species. For example, we have a lot of material based on copper iodide. We can use fluorescent molecules, or we can use organic ligands, not necessarily fluorescent, to turn the band gap of the bulk material so that we can tune the color. As you can see, we have a full rainbow color. So there are two types of materials that we're developing in the lab.
And for the white light that consumers prefer, what kind of wavelengths are you looking at?
Well,
and how do you achieve that?
The visible spectrum is roughly from 400 nanometer to 700 nanometer. So if you have a material that emits in that region and covers that region, that will give you white, and that's an almost perfect white. But a lot of cases in commercial lighting, the white color is not perfect, meaning you can cover the blue region and the yellow region, that gives you some sort of white. Or you can add some ingredients in the red region, that will give you a better white. So roughly, if you cover from 400 to 700 nanometers, you can have white light.
Okay, thank you.
Thank you.
Matt Gunther, Chemistry World. I was wondering more about how you actually went about synthesizing this MOF with your other compound, and whether you experienced any difficulties with that, or what were the conditions challenging that you had to synthesize the compound in. And my other question was, although you're saying that the efficiency relative to rare earth phosphors is attractive, how much of the light is actually attenuated by the phosphor? Is there any sort of reduction in the intensity of that light from the original blue LED that passes through the phosphor coating?
Thank you. That's a good question. Let me break that question down into different pieces. So the first part you ask, how do we synthesize our compounds, and are there any difficulties? Well, based on the variety of different fluorescent ligands we can use, if we try and synthesize each and every possible combination, it's not a very effective way to make compounds. So what we use is actually a computational approach first. We actually use both computational and experimental approaches. We first computationally screen our phosphor candidates. We screen a pool of fluorescent ligands. And then from computational results, we can see, we can roughly estimate the emission of each ligand we're interested in. And then we narrow down our choices. Then we use a solvothermal approach under mild conditions to assemble the organic phosphor, the organic ligand, with a metal to immobilize the organic ligand into a solid structure, into a rigid structure. And that's our approach. The difficulty is, well, as I might describe the process to be very easy, it's like a recipe. If you know the recipe is easy, if you don't, you have to figure it out. meaning you can't simply expect to mix one and two together and get your targeted compound. You always have to tweak your recipe. Sometimes you need a solvent, sometimes you need a specific temperature. But finding that solvent and temperature is not easy. But once you have the recipe, the cooking is relatively easy. And the last part of your question is, so my understanding is you're concerned the energy consumption from the excitation source and how much of that energy pass through the phosphor and get wasted. Well, we actually measure the overall performance of a light bulb. So if we go back one more slide, for example, the LED bulb we study here, we can actually measure the term, I believe the term is called luminance efficacy. That measures the performance of how efficient your LED is. And I think the number that we have, is above the threshold established by the US DOE that is efficient enough to be used in indoor lighting. And if you allow me to look at my reference, I can give you that number. So let me see. That number of that LED bulb is close to 60 lumens per volt. So that's above the DOE threshold. And the DOE threshold for directional lamp is 40, and ours is 60.
Do we have any other questions? Yes.
Katie Cottingham, ACS News Service. I was just wondering when you thought this LED bulb might be available in stores for consumers to purchase.
We hope soon. But from a research lab to commercialization, there is always a long way to go. Speaking of that, we actually have a granted US patent and several PCTE patent applications filed on this technology. So we're hopefully that we can collect our patents and make our way to commercialization. And we're actually, we're currently actively looking for research collaboration and commercialization. Thank you.
All right, great. I think that's it for this session. Thank you so much, Dr. Hu.
Thank you, it's a pleasure.
The archived version of this session will soon be posted at bit.ly/ACS Live Boston. Please join us for our next press conference today at 9:30 a.m. to hear about a new approach to removing CO2 from the atmosphere and turning it into carbon nanofibers. Thank you.